Now today, let's have a look at the regression and least squares. So in this lecture, we will tap more into the mathematics on how to do the regression modeling, how to estimate the model parameters. So introduction to regression. Our goal is to express the relationship between two or more variables by a mathematical formula. And we have x. So here x is the predictor. Predictor is an independent variable. And this is also the input variable. And this is the output variable. Y is the response variable. And response variable is also called a dependent variable. We specifically want to indicate how y varies as a function of x. So yx is considered a random variable, so it can never be predicted perfectly. Now let's have a look at an example. We're trying to relate the shoe size to the height. So the problem is the footwear impressions are commonly observed at crime scenes. While there are numerous forensic properties that can be obtained from these impressions, one in particular is the shoe size. The detectives would like to be able to estimate the height of the impression maker from the shoe size. So this is a regression problem. So here the x-axis is the shoe size, and the y-axis is the height. And we can see these are the data points we connected. So we want to determine height from the shoe size. So what is a predictor? Our predictor, so here is our predictor. We only have one predictor and one response. So this is a simple linear regression. Predictor is shoe size. Response is the height of the impression maker. So can the height of the impression maker be accurately estimated from the shoe size? So if the shoe size is 11, what would you advise the police? So what if the shoe size is 7, size 12.5? So here we need a regression model. So we assume the true model is of the form yx equals to mx plus epsilon x. So here mx is the systematic part, mx is deterministic, and the arrow epsilon x is a random variable. So the deterministic part plus a random variable, which makes yx is also a random variable. So what caused the error? There are measurement errors and natural variations due to exogenous factors. The error is additive. So in the modeling, the mean could be a sinusoid function. So here is the sinusoid function, and this is our error. So this red line in general is our deterministic part or systematic part. So if we know the amplitude of sinusoid function, angular frequency, phase, and then plus the random arrow epsilon x, we will be able to generate yx. So those dots are y for each x. So suppose for this x, and we have a yx. Yx has a deviation from the mean. So this red part is mx, and this is my epsilon x. Okay. So regression modeling, we want to estimate the mean mx and possibly the distribution of epsilon x. So the distribution of epsilon x is the envelope that we discussed in the previous lecture, that we want to cover most of the that's the confidence interval we want to estimate. So there are two general situations. The first one is theoretical models. So mx is of some known or hypothesized the form, but with some parameters unknown. For example, if we were given the sinusoid function with a omega phi unknown. And the second one is empirical model. mx is constructed from the observed data, for example, the shoe size and height. So we often end up using both constructing the model from the observed data and the prior knowledge. So the standard assumption, the assumption in this modeling is this is a deterministic part, systematic part, and this is a random error. And there are three assumptions. This is assumption 1. The random error, the mean, should be equal to 0. And we have this is a mean 0. Second one is the variance is a constant, sigma square, so which is also homoscedastic. And the covariance should equals to 0. That means there should be uncorrelated. The variance, the residuals, the errors should be uncorrelated. We should not observe any patterns in the errors. So this assumption are only on the error term. This is my error term. We use this y minus the deterministic part. We got the error term. So residuals. So previously, this one is the underlying model. This is a population model. And this is m hat. If we add a hat, this is called estimated model. So if we use the data minus the estimate model, we got this term. This is not epsilon anymore. So this epsilon is called error. And this e is called residue, and which is also the estimation of an error. Two different parts. So if the model fit is good, the residues should satisfy our three assumptions. So the first one, mean should equals to 0. And the first one, you see we have a group of points over here, a group of points over here, and the mean has some big variations. So this group, the mean is over here, this group mean is over here, and this violates the assumption 1. However, for this one, we didn't see any specific pattern in the residues, and the mean is 0. This satisfies the assumption 1. And the second one, we want to have a constant variance. And this one is constant variance, right? From the beginning to the end, the variation is about constant. But for this one, the variation is increasing. So this is not a constant variance. So if we get a residues in this form, this violates the assumption 2. And this satisfies the assumption 2. And the third assumption is the residues should be uncorrelated. But here, you see residues, they are correlated. Here, we see some random variation in this range. So this one satisfies, and this one violates. It's correlated. That means the points, they are related to each other. But here, we see a random noise, and we didn't see any specific correlation between those points. Now back to the shoes. How can we estimate mx for the shoe example? So non-parametric, for each shoe size, take the mean of the observed heights. And the parametric, assume the trend is linear. So the non-parametric approach is we have, for example, if we have for shoe size 13, we have this bunch of dots, and then we do the average for this one, then we got the mean of observed height, and this is non-parametric, and we often call it k-means. Okay, k-means approach, non-parametric approach. And a parametric approach, we assume the trend is linear. So simple linear regression assumes the mx is of the parametric form beta 0 plus beta 1x, which is the equation for a line. So what is beta 0? Beta 0 is the intercept of the line. And what is beta 1? Beta 1 is the slope of the line. So now in this equation, we have y equals to mx plus epsilon x. And this y, in simple linear regression, this becomes y equals to beta 0 plus beta 1x plus epsilon x. Okay, so this is simple linear regression model. Now there's a question, which line is the best fit? So here we have 3 lines, and they have different intercept and different slope. Now, which line gave us the best fit? And what is the criteria that we can evaluate how can we tell which one is the best? Okay, so write the observed data yi equals to beta 0 plus beta 1 xi plus epsilon I. So here y is the response value of the observation. Beta 0 and beta 1 is unknown parameters, and x is the predicted value for observation I, and this epsilon is the random error for the observation I. So now we want to estimate parameters in linear regression, and this is statistic decision theory. Now suppose we have g x beta to be an estimator for yx, and we want to define the loss function, so which describes how far gx is from yx. So this is a squared error loss function. So yx is the data and gx is the estimator. So the best predictor minimizes the risk, that is expected loss. Okay, so g star x equals to, we want to find the estimators that give us the smallest squared error loss. So now in simple linear regression, we have the data and we have the xi and yi. This is the response and this is my predictor. And this is a model. And the y minus beta 0 plus beta 1 xi. And this whole term is actually my epsilon I. So the loss function is actually, we want to minimize the errors. So an approximation to the risk function is the sum of the squared errors. That means for every data points, we want to find the epsilon I and we want to sum them together, and we want to minimize this function. So this is called, so what is the R? This term is called RSS. This is called residue, and this S is sum, and this is the square. So this is the residue sum of squares. So this is RSS. So here, this is the residues, and this is a sum, and this is a square. Then it makes sense to estimate beta 0 and beta 1 as the values that minimize this function, the residue sum of squares. So we want to find beta 0 and beta 1, which minimize this function and give us the best estimate. So here, this is our loss function, RSS. We are going to differentiate the risk function with respect to the unknown parameters, beta 0 and beta 1, and then we equate this equation to 0. And so you see this equation, we know this xi, yi, xi, and what do we want to solve is beta 0 and beta 1. And we have equation 1 and equation 2, we have 2 unknown parameters. So we can solve these 2 equations for these 2 parameters. And this 2 equation is also called normal equations. Now, by solving the two equations, we will be able to get the least square estimate. So this is LSE, so we call it least square estimation. We will be able to get the beta 1 hat and beta 0 hat. So here we have x bar and y bar. They are the sample mean of the xi's and yi's. Now, based on the least square estimations, that means each yi, we have yi here, and yi hat is right over here. So we want to minimize the residues, all the residues from model prediction. And the least square estimation tells us the beta 0 equals to 51.46, beta 1 hat equals to 1.62. So this is the best line. That is, best line is line 2. Which one is line 2? So this is the red one is line 2. That is give us the best fit. So how define the best? Best is the residue sum of squares is the minimal. It's the smallest. So this line gives us the minimal residue sum of squares. So residues, we have yi hat. So this is a fitted value, model prediction. And the residues equals to the difference between the observed and the fitted value. And we can use the residue to check whether the three assumptions. What are the three assumptions? A1, A2, A3. This is mean 0. This is a constant variance. And this one is uncorrelated. Okay, so three assumptions. So here we check the, this one is also called, after we plot it, this is called residue analysis, which is also called model diagnostics. So model diagnostics, we want to check our residues to see whether three assumptions are satisfied so that we can see whether the model is valid or not. So here we can see we have approximately the mean is 0, and we have approximately constant variance, and the data points are pretty random and this is not correlated. So now let's have a look at some kind of pool fit. Okay. So these are examples of the pool fit. Suppose we have this is x and this is y, and if for this kind of data, okay, if we still use the linear regression to fit it, then we will be able to, these are the residues, and we plot the residues. So this is x, and this is a residue plot. So if we see the residue plot, we see the residue has some kind of patterns. So this is an example of the pool fit residue plot, residue analysis, or model diagnostics tell us the model is not adequate at all. Now in this case, we see a polynomial or trend in the residue plot over here. So we want to increase model complexity. So what we do is adding polynomial terms in the linear model. So we modeling the mean trend as a line does not seem to fit extremely well in the above example. So there is a systematic lack of fit. So we consider adding the polynomial terms. So previously we only have these two terms. Now we add the polynomial terms. So in this case, instead of x and y, xi and yi, now we have xi square and 2xi piece term, piece power to yi. So we have more columns in the regression. But this is still considered as a linear model. Why? Because M is a linear combination of the beta. Okay, so but there's a danger of overfitting because we include too many terms. Now, if we consider a quadratic fit, so this one is a quadratic fit, and we add the x power 2 term in the model. Now this will be this is the model. And this is a simple linear regression model. So this is a first order and quadratic term. And if we check the residues from each data point, each observation to the model prediction, for example, from here to here, this is my residue. This is residue again. This is a residue. And if we plot these residues, and we will be able to see this is a quadratic fit residue plot, and we see the constant variance. So we check A1 being 0, satisfied, A2 constant variance, satisfied, A3 uncorrelated, satisfied. But this is the quadratic term, and this is the simple linear regression. So this is x, and this is y, and this is my regression line. And if we check the residues, we see A1, is it constant? Is the mean 0? Okay, mean is 0, but A2 is the variance constant? Is not. A3, it is uncorrelated? No, it is correlated. So this one, it is the three assumptions. Model diagnosis tell us this model is not a simple linear regression model, is not a good model for the data we have. But the quadratic model is a good model, but this is not a good model. Now here, let's have a look at the matrix approach to least linear least square. Previously, we wrote our data as yi equals to beta 0, beta 1x1, beta 2x2, beta pxp if we write in the summation term. And why we have k0? Because we have a intercept term. So this is our model. So in matrix notation, we will have y equals to x beta plus epsilon. So here y is all the response variable, and this is my predictor matrix. And how many parameters we have? That is p plus 1, y plus 1, because we need an intercept term. And those are the arrow terms. So how many parameters are in the model? P plus 1. So n, so this n is the number of observations, or we can call it sample size. So to minimize the sum of squared errors, we use the risk function, that is the y minus x beta transpose times y minus x beta. And this actually is equivalent to the matrix transpose epsilon, transpose epsilon. So taking derivatives with respect to beta gave us the normal equation. So this is so we want r beta over beta equals to 0, but this is in the matrix term. So we will be able to get this one. This is our new normal equation. So if we multiply this x transpose, for example, x transpose x inverse x transpose x, and then beta equals to x transpose x inverse x transpose y. However, you see, this term will become an identity matrix. So that's how we got this least square solution for beta. That is x transpose x inverse x transpose y. This is a LSE estimation of beta for multiple linear regression model. Okay. So far we have finished the simple linear regression, and then we talk about how to add the quadratic term or polynomial term to the model. Then we extend it to the multiple linear regression model, and also how to estimate the model parameters. We talk about one approach, which is called LSE, least square estimation. That is, minimize the residue sum of squares and find the beta to minimize the residue sum of squares. Then we got the best estimation of the beta. And after the modeling, we need to do the model diagnostics. And how to do the model diagnostics? That is to perform the residue analysis. We check 3 assumptions. A1, mean 0. A2, constant variance. A3, uncorrelated. Okay, so this concludes the second lecture on linear regression.